Welcome to this comprehensive guide on design patterns in Go, specifically focusing on structural patterns. Today, you will master 3 essential structural design patterns: the adapter pattern, the decorator pattern, and the facade pattern. These patterns are fundamental building blocks that leverage Go's powerful interface system and composition features to create maintainable, scalable, and elegant code. Structural patterns are all about organizing and assembling objects and classes into larger structures while keeping them flexible and efficient. By the end of this tutorial, you will understand how to bridge incompatible interfaces with the adapter pattern, add behavior dynamically using the decorator pattern, and simplify complex systems through the facade pattern. Let's dive into the world of Go's structural design patterns. The adapter pattern addresses a common problem in software development. What happens when 2 interfaces are incompatible but need to work together? Imagine you have legacy code that uses one method signature, but you need to integrate it with a new API that expects a completely different interface. This is where the adapter pattern shines. The problem occurs frequently when working with third-party libraries that have different method signatures than what your application expects, or when you need to make legacy code work with modern systems without modifying the original source code. The solution is elegant. Create a wrapper that acts as a translator between the incompatible interfaces. The adapter pattern allows you to bridge these incompatible objects using Go's interface system, enabling you to compose existing functionality without changing the underlying source code. This approach improves code reusability and maintains backward compatibility. The decorator pattern is a powerful structural pattern that allows you to add behavior dynamically to objects without modifying their original structure. Think of it like gift wrapping. You can wrap an object in multiple layers, where each layer adds new functionality while preserving the core object underneath. The core concept revolves around creating wrapper objects that implement the same interface as the original object, allowing you to stack multiple decorators for layered functionality. This pattern is particularly useful when you want to add features at runtime without using inheritance, which can become unwieldy with multiple combinations of features. The behavior of the decorator pattern is to stack multiple decorators, where each decorator enhances the original object with additional capabilities. The beauty lies in its flexibility. You can combine decorators in different ways to achieve various functionality combinations, all while maintaining the same interface contract. The facade pattern serves a crucial purpose in software architecture, providing a simplified interface to complex subsystems. Imagine a home theater system with multiple components like audio systems, video players, lighting controls, and streaming devices. Instead of requiring users to interact with each component individually, the facade pattern creates a single, unified interface that coordinates all these complex operations behind the scenes. The primary purpose is to hide complexity behind a single entry point, making libraries and frameworks much easier to use for client applications. This pattern is especially valuable when dealing with legacy systems or third-party libraries that have complex APIs. The benefits of using the facade pattern are significant. It reduces coupling between clients and the underlying subsystem, promotes loose coupling throughout your application, and greatly improves maintainability by centralizing the interaction logic. The pattern follows the principle of providing one interface to rule them all, simplifying the client's interaction with complex systems. Let's examine a concrete implementation of the adapter pattern in Go. Here we have a legacy interface called oldPrinter with a method called printOld that takes a text string and prints it in an old format. This represents existing code that we cannot modify but need to integrate with our new system. The adapter implementation creates a bridge between the old and new interfaces. First, we define a modern printer interface with a print method that follows our current naming conventions. Then, we create a printer adapter struct that contains a reference to the old printer. The adapter implements the new printer interface, but internally delegates the work to the old printer's print old method. This way, client code can use the modern printer interface while still leveraging the existing functionality of the legacy old printer. The adapter acts as a translator, converting calls from the new interface format to the old interface format seamlessly. Now let's look at a practical implementation of the Decorator pattern using a coffee ordering system. We start with a base coffee interface that defines two methods: cost, which returns the price as a float 64, and description, which returns a string describing the coffee. The simple coffee struct implements this interface with basic functionality. It costs $5 and has the description simple coffee. This represents our core object that we want to enhance. The decorator implementation shows how we can add features dynamically. The milk decorator struct contains a reference to any coffee interface, demonstrating the power of composition in Go. When we call the cost method on the decorator, it adds $1.50 to the base coffee's cost. Similarly, the description method appends milk to the existing description. This pattern allows us to create multiple decorators for different add-ons like sugar, whipped cream, or extra shots, and stack them in any combination while maintaining the same coffee interface throughout. Let's examine how the facade pattern simplifies complex system interactions through a home theater example. We start with multiple complex subsystems, an audio system and a video system, each with their own turn-on methods that print status messages when activated. These represent the individual components that would typically require separate interactions from the client. The facade implementation creates a unified interface through the home theater facade struct, which contains references to both the audio and video systems. The key method is watch movie, which orchestrates the entire process behind a single, simple interface. When a client calls watch movie, the facade internally handles turning on the audio system, activating the video system, and providing a friendly message to the user. This eliminates the need for client code to understand the complexity of coordinating multiple subsystems. The client simply calls one method and gets a complete, coordinated experience. This pattern is particularly powerful in Go because it leverages composition to hide complexity while providing a clean, intuitive API. Go's interface system and composition model provide the perfect foundation for implementing structural design patterns effectively. Interfaces in Go define behavior contracts without requiring explicit implementation declarations. Unlike many other languages, Go uses implicit satisfaction, meaning you don't need an implements keyword. If a type has the required methods, it automatically satisfies the interface. This enables powerful polymorphism and promotes loose coupling throughout your application design. The interface system allows you to define what an object can do without specifying how it does it, creating flexible and testable code. Composition in Go involves building complex types by embedding other types, following the principle of favoring composition over inheritance. Since Go doesn't have traditional class inheritance, composition becomes the primary mechanism for code reuse and creating modular designs. You can embed structs within other structs, automatically promoting the embedded types, methods, and fields. This approach creates flexible and modular designs that are easier to understand, test, and maintain compared to deep inheritance hierarchies. Implementing these structural patterns in Go provides numerous practical benefits that directly impact your software development process. Maintainability is significantly improved because these patterns promote clean separation of concerns, making your code much easier to modify and debug. When each component has a well-defined responsibility, tracking down issues becomes straightforward, and making changes doesn't create ripple effects throughout your codebase. Scalability becomes achievable through interface-based design, which enables horizontal scaling of functionality. You can add new implementations of existing interfaces without modifying existing code, allowing your system to grow organically. Testability is greatly enhanced because interface contracts make creating mock implementations trivial. You can easily substitute real implementations with test doubles during unit testing, leading to faster and more reliable test suites. Flexibility is perhaps the most significant benefit. You can swap implementations without breaking client code. This means you can optimize performance, add features, or integrate with different systems by simply providing new implementations of existing interfaces, all while maintaining backward compatibility. Congratulations! You have now mastered the 3 essential structural patterns in Go. Let's recap what you've learned. The adapter pattern helps you bridge interfaces when you need to make incompatible systems work together without modifying existing code. The decorator pattern enables you to layer functionality dynamically, adding behaviors at runtime while maintaining the same interface contract. The facade pattern allows you to simplify complexity by providing a unified interface to complex subsystems. These patterns work exceptionally well in Go because of the language's powerful interface system and composition model. By leveraging Go's interface system and composition, you can create maintainable, scalable, and testable applications that stand the test of time. These patterns are not just theoretical concepts. They are practical tools that solve real-world software design challenges. As you continue your Go development journey, remember that these structural patterns provide the foundation for building robust applications that are easy to understand, extend, and maintain. Master these patterns, and you'll be well-equipped to tackle complex software design challenges with confidence.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.